Okay, in this lesson we're going to talk about complex conjugate zeros of polynomial functions. For a polynomial function f of x with real coefficients, if a plus bi is a zero of f of x, then a minus bi, its conjugate, is also a zero. Okay, so we're going to look at two examples of where this comes into play. First example says write a polynomial function of minimum degree in standard form with real coefficients whose zeros include -3, 4, and 2 minus I. Okay, so they give us 3 of the zeros, and they want us to come up with the equation of a function in standard form that has these zeros. So the first thing we're going to do is start with factored form. If we have the zeros, or some of the zeros, then we can put them into factors. So if -3 is a factor, then x plus 3 is going to be, or excuse me, -3 is a 0, x plus 3 is going to be a factor. If 4 is a 0, x minus 4 is going to be a factor of our function. And if 2 minus I, then x minus 2 minus I is going to be a factor. Now remember, from what we just talked about, if 2 minus I is a 0, then its conjugate is also a 0. So even though they don't list it, x minus 2 plus I is also a factor of this function. Okay, so making sure we go back and read our directions, they don't want this equation in factored form, they want it in standard form. So we need to multiply these factors through and get descending degree order. So I chose to do the first two together, put them in a box, and the second two together, put them in a box. So we get two trinomials. We get x squared minus x minus 12 times x squared minus 4x plus 5. So then if we multiply those to each other, we got a 3 by 3 box. We end up with x to the fourth minus 5x cubed minus 3x squared plus 43x minus 60. Okay, our second example says find all zeros of f of x equals x to the fifth minus 3x to the fourth minus 5x cubed plus 5x squared minus 6x plus 8, and write f of x in its linear factorization. Okay, so in this problem we're given a function, a polynomial function in standard form, descending degree order. They want us to, in a sense, factor it. Okay, we don't have a graph. Unfortunately, we don't have our graphic calculators handy, so that we can maybe look at some of the zeros, the x-intercepts. So we're going to do it by hand. We're going to start off with our p over q method, our p being the constant 8, and our q is the leading coefficient. And then we look at all of the multiples, just like we did earlier in this unit, and we're going to look at all of the combinations of the multiples of p over the multiples of q. Okay, and here's what we get. Thankfully our q is 1, so we don't have to deal with any fractions. So we've got 1, 2, 4, and 8, and then the opposites of each. Okay, so these are our 8 possible rational roots. Okay, so now keeping in mind, since the degree of our function is 5, we should expect 5 roots total, but these are just the possible rational roots. So we should not necessarily expect to get 5 of these as our roots. All right. So we've got our 8 possibles. So we go through and do synthetic division. I went through and did 1. I kind of just started on the top and went through. Found out that 1 happened to be a 0. Okay, so using synthetic division, when we find a 0, then we can use that last row for the rest of our synthetic division. Okay, so I brought down that. I tried 2, that didn't work out. I tried 4, and 4 was also a 0. And if you notice that the last row is all non-negatives, so that means that 4 is an upper bound, so I don't even need to take the time to try 8. Okay, so I went down to our negatives, tried -1, didn't work out. Tried -2, -2 is a 0. And notice that they alternate non-negative, non-positive, non-negative, non-positive. So that means that negative 2 is a lower bound. So that means that negative 4 and negative 8 cannot be 0. So I don't have to waste the time testing those using synthetic division. So I've got 3 rational roots, 1, 4, and negative 2. So 1, 4, and negative 2 are the rational roots. So what do we do with those? What we can do is we can take these as 3 of our roots. We still need to find these 2 roots though. So if we take this last row, then 1, 0, 1 is the same thing as x squared plus 1. Set it equal to 0. Okay, so we've got a quadratic. Remember, whenever we get that synthetic down to 3 numbers, then we can go straight to our equation and solve for that quadratic. So solving for x, subtracting 1 on both sides, square root both sides, we get x is equal to the positive or the negative I. Okay, so those are our 2 complex roots. So we've got 1, 4, and negative 2, and we've got positive I and negative I. So if we want to come up with the linear factorization, then we've got our 1 root, x minus 1, our 4 root, x minus 4, our negative 2 root, x plus 2, and then we've got x plus I and x minus I.